Hello and welcome to the lecture over 1.1 Deductive versus Inductive Reasoning. This is your view of the class setting. You would start off at the welcome page. If you want to access this PowerPoint for later viewing, you can go to access any of the PowerPoints. At PowerPoints, click on the chapter, and today we're going to talk about 1.1. Chapter 1 is logic, and in 1.1 we're going to focus on deductive versus inductive reasoning. We're going to use Venn diagrams to determine the validity of deductive arguments, and we're going to introduce inductive reasoning to predict patterns. The first thing we're going to talk about is deductive reasoning. Once a problem has been defined and analyzed, it might fall into a known category of problems. So a common method of solution may be applied. And this is seen a lot of times in mathematics. They say, oh, I know how to do this type of problem. In the past, I do steps 1, 2, 3. I'm done and I have the conclusion. Example 1 in your ebook, or if you bought the textbook in the UMKC edition, it's on page 4 and 5 of either your hard copy book or on the ebook. And that's applying deductive reasoning to solve a quadratic equation. Now in this class, I'm not going to ask you to solve quadratic equations. I might ask you to classification of the logic used to solve it, and in this case is deductive reasoning. I'm taking a general quadratic equation. I'm applying the quadratic formula for it. I know I can apply the quadratic formula to it because it is a second order equation in one variable. Therefore, the quadratic formula is going to be able to solve it. So you can look at example 1 in your book and go through and see the solution, but again, you're not going to have to do that type of work. You're going to classify reasoning as inductive or deductive. So the way deductive reasoning worked is we applied a general rule to a specific case. So the general rule is saying that quadratic formula solves second order equations. The specific case would be the equation we were given. That this specific equation falls under the general rule, so we can solve it. This is known as deductive reasoning, and we're going to have a figure that summarizes this later on. Logic is the history of logic. If you take a logic class, you'll learn about syllogisms, premises, and conclusion. Again, we're not going to focus on defining these terms. We're going to focus on, given a statement, is it valid or invalid? So we want to focus on how do we know if a statement is valid or how do we know it's invalid. So for any given premises, that's going to be the major and minor premises of if the conclusion of the argument is guaranteed, then it's valid. If it's not guaranteed, it's invalid. So we'll do examples of drawing Venn diagrams to show you whether it's guaranteed or not guaranteed. One of the best known Aristotle's syllogisms would be the statement or the premise, all men are mortal. The minor premise, Socrates is a man, therefore Socrates is mortal. When the major premise is applied to the minor premise, the conclusion is inescapable. The argument is valid. This is the example number 1 of the quadratic formula, what I talked about before. Anytime you have this general form, if A, then B, and then your minor premise is saying all x's are A or x is A, you can make the conclusion that x has to be B as well. So we can see this in a Venn diagram, and a Venn diagram is a diagram consisting of various overlapping figures contained within a rectangle. So we say everything in the universe fits in this rectangle, and then inside the Venn diagram, we have all the elements in the universe that fits under B and all the elements in the universe that fits under A. If we have all A are B, you see all the elements inside A also have to be inside B. There's no escaping being inside B if you're inside A. So the statement all A are B, if A then B, we can draw 2 circles that look like this. However, if something is said no A or B, we do 2 disjoined circles. They have no overlapping area. If some A are B, then we have some overlapping area and some not. So we draw a Venn diagram like this. The example we talked about before, all men are mortal, Socrates is a man, therefore Socrates is mortal, can be drawn in a Venn diagram like this. There's no escaping anyone in this category being mortal. Therefore, the conclusion is valid because it's inescapable. So X being Socrates, Socrates has to be in this circle somewhere. So Socrates has to be in this circle somewhere, so he has to be in the mortal circle. So the argument is valid. Saying that an argument is valid does not mean the conclusion is true. Does not mean that. It just means that given the premises, that the conclusion follows. So if we want to look at the whether an argument is valid or not, we won't determine if it's true or false, only if it's valid given the information. So just given the premises, the reasoning used to obtain the conclusion is logical. However, if the premises of a valid argument are true, then the conclusion will also be true. So that's important. If you know the premises are true, then the conclusion being valid has to also be true. But if the premise is false, then the conclusion can still be valid but not true. So that's something to think about. And it doesn't really come up much in our homework, but in logic it comes up quite a bit. Saying that an argument is valid does not mean that the conclusion is false. Invalid does not mean the conclusion is false. In logic, whether something is valid or not and the truth do not have the same meaning. So it only something being valid or invalid only refers to the process of the reasoning. So this is kind of lawyer speak here. You have to be careful with that. Used to obtain the conclusion. True refers to whether it's a fact or experience. So if it has been confirmed as a fact or confirmed as someone's experience. Venn diagrams help to do this. The next example we're going to look at, some plants are poisonous. Broccoli is a plant, therefore broccoli is poisonous. Well, we know broccoli is not poisonous. So we know it's a false statement, but it could still be valid. And it turns out we have the example plants and poison. So we have some plants are poisonous. Broccoli is a plant. So sure, broccoli could be in this area, and in that case, this area would be a poisonous plant, but broccoli could also be in this area. So it is escapable that broccoli has to be poisonous. So therefore, we would say that the argument is invalid based on the picture we drew, the Venn diagram. Inductive reasoning is not as guaranteed. So if I say Joe sneezes after petting Franco's cat, Joe sneezes after petting Paulette's cat, therefore Joe is allergic to cats. This is not guaranteed. This is just using specific examples for a generalized statement. Conclusions are not guaranteed, so that's important to know. It's not guaranteed to be true. If the premises are true, they are certainly supported by the conclusion, but we cannot say with 100% certainty that Joe is allergic to cats. Therefore, the conclusion is not guaranteed. Maybe Joe is allergic to flea powder, or that the cat owners used, or maybe he's allergic to dust that is trapped in the cat's fur. Maybe he has a cold. Again, the reasonings can go on forever. So really what we want to focus on is deductive reasoning. The conclusion is guaranteed. We're taking a general statement and we're applying it to a specific example. In inductive reasoning, we're taking a specific case or specific example and we're applying it to a general statement. The conclusion is not guaranteed. So this is an example of inductive reasoning. What number will come next in the sequence? Well, a lot of people say, oh, they're just adding 7. So we would expect maybe 36 to come up in the sequence. The solution is not guaranteed because a different sequence could also be true. For instance, the date of Saturdays in the year 2011 were January 1st, January 8th, January 15th, January 22nd, January 29th, February 5th, and so forth. So it might be 5 might come next in the sequence. It would be, without further information, we cannot determine the next number of the given sequence. We can only use inductive reasoning to give one or more possible answers. So sometimes there might be more than one answer out there. So these are examples that come up in your homework. Find the general rule or pattern used to assign the given letter to the given word. So this is using inductive reasoning to induce what the answer would be here. So if you notice, I have circle, I have square, I have trapezoid, and octagon. The first vowel of each one of these words is the answer. So I would expect I to be the answer for triangle. This one is a little bit different, but it's the same, along the same concept. If I look at the vowels, I have I, J, U, V, A, B, O, P, so I expect this to be I, J. And on your homework, you can click this Watch It button and it will explain the problem. Some of the problems will be randomly generated as we get going through the semester if we do anything with numbers or anything later on. Just watch it. Will explain the given problem, but it will be randomly generated, so it might explain with different numbers. In section 1.1, it's pretty straightforward as far as the watch-its are the problems given. You will not have the watch-its on the quiz, so keep that in mind. If you rely a lot on the watch-its, then you really need to use the watch-its to understand what's going on, but don't rely on them to do your homework. Keep in mind, once you get used to seeing the kind of problems asked, it should go, straightforward. Think of like days of the week, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, starting at any one of those. Think of months of the year, January, February, March, April, May, so forth. This example, if you think of counting, 1, 2, 3, 4, so you expect this to be 5 and this to be 6. So this is the first letter of each word in counting. So this would be 1, 2, 3, so forth. This example would be classifying the arguments as deductive versus inductive. On page 10 of your book, you have this picture that kind of explains. If you're given a specific case and you're applying it to a general statement, that's inductive. If you're given a general statement and applying it to a specific case, that's deductive. I ate chili dogs at Joe's, I got indigestion. I ate chili dogs at Ruby's, I got indigestion. Therefore, chili dogs give me indigestion. Those are specific instances, and then I'm making a general statement. So this is going to be inductive reasoning. All spicy foods give me indigestion. That's a general statement. Chili dogs are spicy food. That's a specific type of spicy food. Therefore, this would be deductive reasoning that chili dogs give me indigestion. So hopefully this helps on your 1.1 homework. The 1.1 homework is due August 26th by 11:59.